In this video, I am going to start by discussing electronegativity. We're then going to go on to look at polar bonds and intermolecular bonds, which it all follows very neatly on one from the other. So starting with electronegativity. This is a term that is just used to describe the power of an atom to attract electron density in a covalent bond towards itself. If we start by a simple covalent bond, one between oxygen and hydrogen, we've got a shared pair of electrons. However, this shared pair of electrons is not shared equally between oxygen and hydrogen. The reasons for this are very straightforward. Oxygen has 8 protons in its nucleus. Hydrogen only has 1. So clearly, that electron density is going to be more strongly attracted towards the oxygen nucleus than the hydrogen. Oxygen is a very electronegative element. We've got a table here. This was put together originally by a chemist called Linus Pauling. Pauling values essentially describe the electronegativity of elements. When you look from one table to another, the figures do vary very slightly. However, that's not important because all we need to recognise is that fluorine is the most electronegative element of all, because it's got 9 protons in its nucleus and it's only got 2 shells of electrons, which means that there is very little, squeeze that in there, there is very little electron shielding. So we haven't got electrons around the fluorine nucleus blocking the nuclear charge to shared pairs of electrons. In terms of remembering which elements are electronegative and which aren't, as long as we focus on the fact that fluorine is the most electronegative element, you can see here that it decreases as we move away from oxygen, nitrogen down towards carbon, from fluorine to chlorine to bromine to iodine. The term electronegativity is used almost exclusively in terms of describing covalent bonds, so we're talking about molecules. A bond is described as being polar if we have an electronegative element bonded covalently to a less electronegative element. So a classic example here is hydrogen chloride. Hydrogen is not electronegative at all. Chlorine is very electronegative. Lots of protons packed into a nucleus pulling the shared pair of electrons towards itself. We can represent that with these 2 symbols. That is a symbol for delta, a small Greek d. Delta positive means that the hydrogen is electropositive. It hasn't got its equal share of electron density, and the chlorine is electronegative. Now, this is a permanent state of affairs in this molecule. This uneven distribution of charge is often described as a dipole, and this molecule has a permanent dipole. There is a permanent uneven distribution of charge across the hydrogen chloride molecule because chlorine is far more electronegative than hydrogen. In my water molecule here, so I've got water, H2O, we can see that I have got 2 polar bonds. I have got 2 uneven distributions of electron density between the hydrogen and the oxygen. Hydrogens are marked with the delta positive and oxygen with the delta negative. If I go back to my table of values, then the bonds that are always going to be polar are going to be the bonds between hydrogen and fluorine, hydrogen, oxygen, chlorine, nitrogen. These are the common ones that we see, particularly in organic molecules. We're looking at carbon fluorine, carbon chlorine, carbon oxygen, phosphorus oxygen, sulfur oxygen. To a lesser extent, maybe carbon or hydrogen to bromine. You'll get really familiar with starting to recognise which are the electronegative elements, and that we're nearly always talking about them being bonded to either hydrogen or carbon. Language is really important in this topic in terms of exam technique, but it's also a little bit confusing. So we have this representation here, dipole, so that's the permanent uneven distribution of charge across the molecule. But the bond itself is often described, or also described, as being polar. In terms of A-level chemistry, we tend to talk about molecules having dipoles and bonds being polar, and although this is not exclusive, that's quite a good way to think about it so we don't get confused. When we are asked to decide whether a molecule has a permanent dipole, we need to run through the stages. So first of all, have we got any electronegative elements? Secondly, are they bonded to a less electronegative element? Have we got that polar bond? How many polar bonds have we got? And what effect does the shape of the molecule have? So let me give you an example here. This is tetrachloromethane, CCl4. Now I know that carbon in the middle is less electronegative than chlorine. So I know I have a polar bond. Chlorine is electronegative. I could represent that particular uneven distribution of charge, that dipole, with my symbol. However, it makes more sense to save that for the molecule itself. However, when I look at the shape of this molecule, because it's tetrahedral, we have got our uneven distribution of charge going out, this one's a little bit more harder to tell, but you get the idea, in equal directions. It's a symmetrical molecule. So all my polar bonds cancel out. This molecule does not have a permanent dipole. It's got polar bonds, but it doesn't have a permanent dipole because there isn't a permanent uneven distribution of charge across the molecule. Let's compare that with chloromethane, so CH3Cl. In this molecule here, I have got a polar bond because chlorine is considerably more electronegative than carbon. And this polar bond is not cancelled out by other polar bonds in the molecule pulling in the opposite direction. This molecule is asymmetric, which means that if I were to draw it as a blob, this is quite a useful way of thinking about it, then I am permanently going to have more electron density at one end of my blob than the other. Because of the shape of the molecule, the chlorine is at the top end in the way that I've drawn it. So this molecule here does have a permanent dipole. It's got a permanent uneven distribution of electron density across the molecule. I'm saying this really slowly because this is the key language. There's no point beating about the bush here. Just use the language that the mark schemes are going to give you the marks for. So, pulling all that together, if I want to find out whether a molecule has a permanent dipole, I'm identifying, have I got, let's change the colour, bit of fun here, have I got an electronegative element? Is it bonded to a less electronegative element? So I have definitely got a polar bond. And then I need to check the symmetry of the molecule. If I were to think of my molecule as a blob, is there always going to be one part or end of the molecule that is more electronegative than the other? If that's the case, I have a permanent dipole. Which brings us on really neatly to our first type of intermolecular bonds. These are the bonds or the forces of attraction between molecules. Not to be confused with an intramolecular bond, so that would be the covalent bond inside the molecule, i.e. between the two atoms. I'm going to take my example here going back to hydrogen chloride. So my hydrogen and my chlorine. I have identified that I have a permanent uneven distribution of charge across my molecules. And we know that opposites attract, so it makes sense that the delta positive end of one molecule would form an attraction with the delta negative end of another molecule. And this is all that there is to permanent dipole, intermolecular bonds. Now, I know that's a bit of a mouthful. When you're writing this in an exam question, you need to use the whole phrase once. Once you've done that, then most mark schemes allow you to abbreviate to PD, but they don't tend to give you credit if you just start off with abbreviation. You've got to prove that you know what you're talking about. Permanent dipole intermolecular bonds are relatively strong intermolecular bonds, but let's be really clear in our mental picture of this. Our molecules are moving all the time, so these attractions are continually being formed and then broken as the molecules move around. Hydrogen bonds are simply a special case in terms of permanent dipole intermolecular bonding. They happen where we have hydrogen bonded to either oxygen, to nitrogen, or to fluorine. These three elements have got a high electronegativity, which means that my hydrogen isn't just delta positive, it's very electropositive. The electron density is spending almost zero amount of time around the hydrogen. It's mostly being drawn very strongly to the oxygen or the nitrogen and the fluorine. The second thing that we need to look for when we're determining whether hydrogen bonding is present or possible between molecules is that my very electronegative atom must have a lone pair of electrons, because a hydrogen bond isn't just a kind of generally strong attraction between two molecules, between a delta positive and a delta negative. It has direction. The bond is very specifically between the delta positive hydrogen in one molecule and the lone pair of electrons on the electronegative atom in a second molecule. This means that hydrogen bonds in terms of strength are somewhere between a permanent dipole and a covalent bond. They are really very strong indeed, which means that a number of hydrogen-based molecules, so we're talking water for example, hydrides of group 1, have very specific properties, such as very high boiling points, because it takes an awful lot of energy to disrupt, to overcome the hydrogen bonds between the molecules, separate them out so that they can boil, as a general example. When we are drawing a hydrogen bond, I'm just going to create a little bit of space here, and this is a really common exam question, and it can be worth up to 4 marks. You need to be very clear that this is directional, so you have to draw it in a linear way. So if I were drawing this out in the exam, I would draw my first water molecule. You must label the delta pluses and delta minuses, and you must show the lone pairs of electrons on the relevant atom, in this case oxygen. The next bit is key. This is a linear force of attraction, for want of a better way of explaining it. So you need to be clear when you draw it that that is what we are showing. And once again, I'm showing the delta pluses, the delta minuses, and the lone pairs of electrons on the relative atoms. So this is linear. Be really, really clear about that. We don't just see hydrogen bonding in water. The other common molecules between ammonia molecules, hydrogen fluoride molecules, for example. We also see it in more complex molecules, and it has quite a large effect on the properties of many organic molecules. Methanol and butanone I'm going to use as my example. So let's look at methanol. This is what methanol looks like. It's CH3OH. And that is how I might draw methanol. However, drawn like that, it's not much use to me because I haven't got the right angles in order to be able to draw the hydrogen bonding that I want to draw. So I'm going to redraw it. We're going to have the carbon and the hydrogen. I know that that's tetrahedral, however I'm going to draw it like so. However, I know that the hydrogen bonding is going to happen through the OH group. So this is the bit I'm going to draw out carefully with my 104.5 bond angle in the bent or the V-shaped non-linear shape around that oxygen atom. I've drawn in my lone pairs. I'm also going to make a point of putting in the relevant delta plus, delta minus. I know the carbon will also be delta positive, but in terms of hydrogen bonding, it's not part of this game, so I'm just going to ignore it for now. Butanone. What does butanone look like? Well, it's a ketone. It's got a carbonyl group. So we have got an oxygen, lone pairs of electrons. We've got a double bond to a carbon. That carbon is bonded to a methyl group and an ethyl group, C2H5. So 4 carbons, but, and then the carbonyl group. I've drawn it like this because I want it to be really clear. Once again, if I just change my colour, I've got my delta negative, delta positive. So this carbon is relevant because it's part of that kind of polar bond. And then I would be able to draw my hydrogen bond between the delta positive hydrogen on one molecule and the lone pair on the oxygen on another. It's a common misunderstanding that both groups have got to be OH or NH. That's not true. What I need is hydrogen bonded to one very electronegative element with a lone pair of electrons, and it's able to make a very strong attraction to the lone pair of electrons on an oxygen, a nitrogen or a fluorine. And that satisfies all the conditions. The one thing you will notice that is I haven't drawn it particularly well because it's not linear, so I would really need to redraw that so that the oxygen, hydrogen, oxygen, oxygen, hydrogen, oxygen are in the same line. Okay, so some molecules are capable of forming permanent dipole intermolecular bonds. A few molecules are capable of hydrogen bonds. All molecules and all atoms that have more than one electron are capable of an instantaneous dipole. So what's happening there? Well, I would like you to imagine your atom or your molecule as a blob. And the electrons are able to move. We know that because the electrons are present in s, p, d, f orbitals. These are three-dimensional, so there's room for our electrons to move around. I like to think of my electrons as being a cloud of bees. If I were to take a snapshot of a molecule, or a series of snapshots of the electron density of a molecule, the likelihood of me making a snapshot where all the electrons in my molecule or atom are completely 100% symmetrically evenly distributed is very, very low indeed. Because my electrons are moving around all the time, then we are going to have a constant series of instantaneous dipoles where the electrons are swirling up one end of the molecule, think about a cloud of bees swarming up one end, swarming back down the other. Where I've got greater electron density, just for a fraction of a second, that end of the molecule is going to be delta negative, which means that the other end of the molecule is going to be delta positive. This is an instantaneous dipole. Once again, language is really clear in terms of the mark schemes of what you can and cannot say. You can't actually talk about clouds of bees or clouds of electrons or swirling, understandably. What we want to talk about is the fact that we have moving electrons or electron movements lead to a temporary uneven distribution of charge, and that is an instantaneous dipole. The instantaneous bit is key because a fraction of a second later, as we can see through my series of pictures here, then all the electrons are going to have moved to a different area of the molecule, and the delta negative and the delta positive will change. All of which brings us neatly to our last type of intermolecular bond, instantaneous dipole, induced dipole intermolecular bonds. This is quite a mouthful. If you are following the OCRB Salters Chemistry A-level, then this is the term they prefer you to use. Once you've used it once, you can abbreviate it, but you will not get credit for just using the abbreviation. You need to prove that you know what you're talking about. These types of bond are also known as London forces. And this is the preferred term for the OCRA. Check your syllabus and your textbook carefully to find out which terminology they prefer you to use. AQA call them van der Waals forces. Now, once again in chemistry, the language isn't tied down. Technically, a van der Waals force, that's with a small v, van der Waals forces, are both permanent dipole, and instantaneous dipole, induced dipole. However, that's not how AQA see it. So just double check on your language. Although having looked at all the mark schemes, there does seem to be some flexibility here. Right, moving swiftly on. If I have a molecule which has an instantaneous dipole, so electron movements are creating an uneven distribution of charge temporarily across this molecule, then that would induce a dipole in a neighbouring molecule. So if all the electrons are swirling up one end of the molecule, don't use the word swirl in an exam, then that would repel the electrons in a neighbouring molecule. It would induce a dipole in a neighbouring molecule. When we're talking about this in terms of exam technique, we need to remember that a bond is an attraction. So the bond is actually this attraction here between the molecule number 1 with my instantaneous dipole and molecule number 2 with my induced dipole. And you need to say all that when we are looking at writing about this in the exam. Lots of students lose marks by explaining how the instantaneous dipole arises, explaining how an induced dipole arises, but not actually going on to say that we have got an attraction between the two. And that is technically what our intermolecular bond is. Now, we need to be really clear that all molecules that have, or atoms that have more than one electron are capable of instantaneous dipole, induced dipole, intermolecular bonds and capable of having London forces. So if I were to take water, for example, just as an example, this is a molecule with electrons, so it is capable of instantaneous induced. It has a permanent dipole. Because of the shape of the molecule not being symmetrical, I know that the electron density is permanently pulled towards the oxygen. So it's also capable of permanent dipole. But as we've seen, water, hydrogen bonds, because of the special scenario where we've got the hydrogen bonded to the very electronegative oxygen and the lone pairs of electrons. You need to be very careful when we are reading exam questions as to whether the question is asking you to talk about all the intermolecular bonds in a molecule or just the strongest type, which is the most common type of question. We can use London forces or instantaneous dipole-induced dipole intermolecular bonds to explain the trend in boiling points for the noble gases. Helium has got 2 electrons. Xenon is a much bigger atom. It's got 54 electrons. If we're talking about the ability of these atoms to produce an instantaneous dipole, then clearly we're able to get a much greater uneven distribution of charge in a xenon atom simply because it has far more electrons. So we explain that in terms of there being stronger London forces, stronger instantaneous dipole, induced dipole, intermolecular bonds. A bit lazy, just call them ID. The strength of London forces, or instantaneous dipole, induced dipole, intermolecular forces, firstly depends on how many electrons we have got. So that regulates the kind of size of the instantaneous dipole, the degree of uneven distribution of electron density across that molecule. And it also depends on how closely our atoms and molecules can pack together. So I've got 3 isomers here of pentane, C5H12. As we move from one to the other, we have a decrease in boiling point, which ties in nicely with the degree of branching of each isomer. And the reason simply is that pentane, in terms of its straight chain isomer, these molecules have got a regular arrangement. They can pack closely together. So we have stronger intermolecular forces between the molecules. My final isomer here at the bottom, because of its shape, it's far harder for these molecules to align or pack closely together. So the instantaneous induced, the London forces, are going to be weaker. If they're weaker, it takes less energy to disrupt them, hence the lower boiling point. So let's pull all this together in terms of our exam technique and the kind of language you should be using to pick up the marks. I've got carbon dioxide here. What type of intermolecular bonding is it capable of? Well, the first thing I'm going to do is to draw it out. I can identify straight away that I have got electronegative element oxygen bonded to the less electronegative carbon. So I have definitely got polar bonds. However, because it's a linear molecule, then the dipoles cancel each other out. So this molecule has no overall dipole. So I know that it's only capable of instantaneous induced dipole intermolecular bonds, or our London forces. I could contrast that perhaps with propanone. Propanone, first thing I'm going to do is draw it out. Once again, I've still got a carbon-oxygen bond, so delta negative, delta positive, but I've only got one bond. It's an asymmetric shape, so I can see straight away that it is capable of permanent dipole intermolecular bonding, and that is the strongest type of intermolecular bond it is capable of. Third example here is methylamine, CH3NH2. What does that look like? Well, if I were drawing it out, I might start by drawing up my methyl group, bond to the nitrogen, and 2 hydrogens. I've got carbon bonded to nitrogen, but I have nitrogen bonded to hydrogen, delta negative, delta positive. Because of the shape of the molecule, and nitrogen being the only electronegative element, I know that this molecule has a permanent dipole. However, I'm also thinking, well, I've got a nitrogen and a hydrogen bonded together, isn't capable of hydrogen bonding. I'm going to draw out my molecule again, and I'm going to change the way I draw it, because if I'm thinking about hydrogen bonding, I need to have access to that lone pair. So let's draw it with nitrogen being the centre of the molecule. It's lone pair, it's bonded to a hydrogen, it's bonded to the methyl group, which I'm just going to draw out as a methyl group because they're not really important in terms of distinguishing the bonding here, and my 2 hydrogens. And then it is much clearer to see my delta positive, my delta negative, my delta positive, and my lone pair of electrons. So this would be capable of hydrogen bonding as well as permanent dipole, and of course induced dipole, instantaneous dipole. So key language in describing London forces or instantaneous dipole, induced dipole intermolecular bonds. The first key thing that we should be talking about is here. We've got movements of electrons producing or creating an uneven distribution of charge across the molecule. There really is no better way, probably is no other way to say it that's always going to pick up the marks. Learn this phrase. That's our instantaneous dipole. We're only halfway through the story. The molecule with instantaneous dipole induces a dipole in a neighbouring molecule. We need to be really clear in our answer that this is happening in 2 separate molecules. And then the third bit, which is often left out, this idea that we have an attraction between the 2 molecules. An attraction between the delta positive end of one molecule and the delta negative in my induced molecule. And drawing pictures is a really good way both to help you describe what's going on and to make it clear that you know what you're talking about. A permanent dipole, we can explain, is the result of a permanent uneven distribution of charge across the molecule because this molecule contains polar bonds. This is due to an electronegative atom bonded to a less electronegative atom. Name the atoms if you've got a specific example in your exam question. And the molecule is asymmetrical or not symmetric. And finally, talking about hydrogen bonds, this is where I do very strongly suggest that you draw out a picture. You often get credit for your diagram, and it gives you something to base your or run your explanation off. So the things that we want to be really clear, we've got hydrogen bonded to a very electronegative atom, in this case oxygen, which makes the hydrogen very electropositive or delta plus. And then this is where most or many candidates' explanations go haywire. We need to be really clear that it's the delta positive hydrogen 1 molecule is very strongly attracted to the lone pair of electrons on the oxygen of a neighbouring molecule. Often when you read candidates' explanations of hydrogen bonding, it's not at all clear that they understand or are describing an attraction between molecules. It sounds very much like we've got an attraction between the delta positive hydrogen and the lone pair in the same molecule, so let's not make that mistake. If this has been useful, hit the subscribe button, the effortless way to support your studies, and by clicking the link in the description below, it'll take you straight to Crunch Chemistry School, where you can access my free maths skills course, complete tuition, and worksheets designed specifically to build your confidence and stretch you. Together we can do this.